relativity, time dilation, and the twin paradox. We are going to cover 4 topics in this video. Number 1 is old-fashioned relativity or Galilean Newtonian relativity. Secondly, we'll talk about the rules for special relativity, we call them postulates. Thirdly, we'll talk about time dilation. And fourth, we're going to look at the twin paradox. So first of all, back in time to the 1800s. Everyone used to use an old version of physics because a very wise man named Albert Einstein hadn't come along yet. You might have heard of him. The old physics was called Galilean Newtonian relativity. In this section, we're going to talk about inertial frames of reference and relative speed, which we call velocity, but you can stick to speed for now. Frames of reference are the perspectives that different people see things happening from. Everyone experiences the world from their own frame of reference, or point of view, just like you see the ice cream truck coming down the street towards you, and your next door neighbour sees it coming towards them, and their next door neighbour sees it coming towards them. Each neighbour sees the truck from their own frame of reference or point of view. An inertial frame of reference means that everything in every reference frame moves in exactly the same way. For example, if you and a friend were to both drop a ball, both always bounce down to the ground and back up again. One doesn't start flying around you in circles, and the other doesn't just hang in the air. This would be weird and a non-inertial reference frame. So now we have our inertial frames of reference, we're going to learn about relative speed. Relative speed is the speed an object looks like it's going from your frame of reference. It depends on whether you are moving or not moving. If you are moving fast, another object moving faster than you may not look to be moving so fast. Have you ever wondered why, when you are driving in a car and there is another car next to you, it doesn't look like the other car is moving? This is because you are both moving the same speed, and there is no difference to cause relativity. To help with understanding this, imagine you've made a herd of elephants angry, and they start stampeding towards you. You'd start running away, right? Now the elephants can run faster than you, so even though you are moving, it looks like the elephants are coming towards you. But they look like they are coming slower than if you, say, stopped running. This is because your frame of reference is moving relative to the elephants. Starting to understand it now? Let's do one more. You are running away from the stampede, and you come across a car. You climb in and start driving away. You're moving faster than the elephants, which is good for you. But when you look back, it looks like the elephants are moving backwards. This is because the speed in their frame of reference is slower than yours. Your relative speed is therefore faster, so they look like they're going backwards. So there we have it, inertial reference frames and relative speed between two objects. And we now understand Galilean Newtonian relativity. Now on to our second topic, the postulates of special relativity. So, what is special relativity? At the start of the 1900s, we meet the genius Albert Einstein. He wrote a book called The Special Theory of Relativity, which is basically a more advanced version of what we just learnt, Galilean Newtonian relativity. We use inertial reference frames again, remember, where everything moves in a rational way, like dropping balls. Another rule we get introduced to is that light travels at a single speed all the time, everywhere in space. So, the postulates are 1. The principle of relativity, and 2. The constancy of the speed of light, that light propagates or moves through empty space with a definite speed, where c equals 300 million meters every second. So the first rule means that the law of physics must be the same in all inertial reference frames. Remember back to our inertial reference frames with the balls that move normal directions? This is the same thing, but it only matters that everything happens the same way, like our ball dropping. But this time, it can go round in circles as long as it does the same in both frames of reference. The second rule means that light always travels at 300 million meters per second through space. It doesn't go this speed all the time, for example when it moves through water, but for special relativity we only care if it's in empty space. So these are our 2 postulates or rules of special relativity. Now on to our third topic, time dilation. Time dilation is a crazy concept that goes against everything you think you know about time, so it can be quite hard to understand. You might have to watch this section a few times. Time dilation means the time taken to travel from point A to point B changes when you go faster or slower. You might think that time is fixed everywhere in the universe, but it isn't. Rather, it changes as you move fast or slow. But first, imagine a rocket ship that is about to fly around the Earth a few times really fast, almost as fast as the speed of light. There is a clock on the ship and a clock on Earth, which both say the same time. For this example, let's say they both say 1 o'clock. When the ship flies really fast and then comes back to the same spot, the clock on the ship will say a different time to the clock on Earth. It might say 2 o'clock and the Earth clock will say 3 o'clock. This means the ship has experienced 1 hour and the Earth has experienced 2 hours. The ship has experienced less time passing than Earth has. This is very weird. We think that both clocks should say the same time when they meet again, meaning that they both experience the same amount of time, but they don't. The time is shorter or dilated, which is why we call it time dilation. This is what Einstein theorized in his book, and no one has been able to prove him wrong, so we think he's right. We'll talk about why this works. Imagine a rocket ship flying above the Earth. At the bottom of the ship is a light bulb, and at the top is a mirror which reflects the light down to the bottom again. You are on the ship, so you see the light travel once up and once down, which is 2 times the length of the ship, right? Now, imagine you're watching from Earth. The ship is moving across, so as the laser beams up, it also travels sideways with the ship. As it reflects back down, it moves across further, so the distance it travels is sideways as well as up and down. This distance is longer than what you saw when you were on the ship. Remember back to our postulates that say the speed of light is always the same? If the speed of light is the same in both of these experiments, the light can't have travelled faster to fit in a longer distance in the same amount of time. Therefore, we know the time it took must be different. When we look at the Earth, the distance is longer, so the time must also be longer. We can look at the maths to help us. Our speed is our distance divided by our time, also written as d over t. Our speed is c, and always the same. So we now have the equation c equals d over t. We saw in the experiments that the time the light travelled was longer when we were on Earth. We'll write our 2 equations next to each other, viewed on the ship and viewed on Earth. Let's imagine our 2 distances are 6 and 8, just to keep it simple. Our time is 3 and our speed, c, is 2. If our 6 divided by 3 equals 2 and 8 divided by 3 equals 2, we've broken the law of mathematics. It just can't be true. If our speed of light can never change, we have to change something else in the equation. So, if we make time bigger in the Earth equation, we can make the speed of light stay the same. Let's make that 3 into a 4. That's much better. 6 divided by 3 is 2, and 8 divided by 4 is 2. We're all happy now. So we see as our distance gets bigger, we make time bigger, so the speed of light can always stay the same. This is the mathematical reason why time dilation happens. Time dilation has been proven too. In 1971, 2 physicists sent 2 very accurate atomic clocks on jets around the world. When they came back, they both showed a different time to the clock on Earth, proving that time actually does pass slower for objects that travel fast in space. Finally, we are going to look at the twin paradox, where time dilation gets complicated, but don't worry, it's not too complicated. So a paradox is a loop that can never work, just like travelling back in time to kill your grandfather before you were born, meaning that you never existed to travel back in time. So you never went back in time to kill your grandfather, so he will still be alive, and you will be born, so you will go back and kill him. See how this can never work? We get a paradox when we think about time dilation with people and spaceships. So if a person flies really fast and experiences less time passing, they will be younger at the end of their trip than they would have been if they stayed on Earth. Let's imagine some twins who are the same age. One twin flies to another planet and then flies back home. When the twin comes back, they are younger than the Earth twin because they have experienced less time passing. But here's where we get into the paradox part. When the Earth twin looks at their sibling on the spaceship, it looks to them like the spaceship is moving. When the ship twin looks to Earth, it looks like the Earth is moving away from them. Because of time dilation, when the Earth twin looks at the ship twin, less time is passing for the ship, and that twin must be younger. But when the ship twin looks to the Earth twin, they're moving fast, and the time is moving slower for them, and Earth twin must be younger. They can't both be younger, right? So how can this work? The twin paradox cannot happen in real life, and we have an explanation for it. In reality, when the ship twin comes back to Earth, they will be the younger twin. This is because the ship has to speed up and slow down when it leaves and returns to Earth's atmosphere. And when the ship gets to the other end, it has to turn around, changing direction. Slowing down, speeding up, and changing direction all mean that the ship is no longer moving at a constant velocity, which means it's also no longer in an inertial frame of reference. Remember that special relativity and time dilation will not work without an inertial frame of reference. This means something very weird and complicated has to happen instead. It is explained by another of Einstein's theories, the general theory of relativity. This theory is very complicated, so we won't go into it, but all you need to know that the ship twin will always come back younger than the Earth twin because the frame of reference of the ship stops being inertial. So there you have it. We've solved the twin paradox. That's it. Galilean Newtonian relativity, frames of reference, special relativity, time dilation, and the twin paradox.